Okay, here we go. We have a goal that pops into our mind consciously or not, and the question of whether we act on that goal, maybe even whether we're even consciously aware of having that goal, depends upon completing a loop. And it's not just going to be completing one loop. It's going to take, a split second to go from the cortex to this brain area 2. Brain area 2, by the way, is going to be the striatum. And then from there to brain area 3, which we're referring to as the basal ganglia output area. And then brain area 4, which you might recall is the ventral thalamus. But again, since right now we're not going to be focusing on the ventral thalamus and the basal ganglia output, let's just not worry about the details of the name at the moment. All right, so you want to complete this loop. Since it only takes 1/100th of a second to get from one brain area to another, about 10 milliseconds, in order to have this goal stay active for even a second, it would take, could take 100 revolutions around this loop. You know what I'm saying? You need to complete the loop in order to keep the idea in mind, certainly to keep it in mind long enough to act on it. If the loop is not completed, then you're not going to act on that goal. And then, the typical situation would be, in that case, your cortex would generate a new goal, something else that you might consider doing. You don't have to consciously consider it because this basal ganglia loop is essentially going to consider it for you. And if the basal ganglia loop basically decides that this is valuable enough to do, the way it's going to tell you is by giving you a feeling of desire or motivation for that goal. The goal you can imagine being represented by a set of neurons. Imagine, a couple thousand neurons that are active all together. They keep each other active, but they really require the basal ganglia loop to be completed in order to stay active. The cortical inputs to the striatum release glutamate. So glutamate being excitatory will cause activation of the striatal neuron. This connection between the cortex and the striatum is really key, because if the loop is completed or not completed largely depends upon whether the cortical neuron successfully activates the striatal neuron. If it does, you've got a pretty good chance that this entire loop is going to be completed. And if it doesn't, if the cortex doesn't activate the striatal neuron that receives it, then the loop is not going to be completed. If we focus in on the right-hand panel, we can say, well, these cortical neurons are releasing glutamate, and we're going to represent glutamate as the green circles. These corticostriatal projections, these neurons are releasing glutamate. Glutamate combined to AMPA and NMDA receptors we're looking at here. And we say, does the striatal neuron fire? Would this scenario that you're looking at here be a scenario where you would expect this striatal neuron to fire? There are plenty of AMPA receptors, so yes, yeah. If you have enough AMPA receptors, you can depolarize, activate that striatal neuron. Yeah, okay. Does the striatal neuron grow more AMPA receptors? When we were talking about plasticity before the second exam, the answer definitely would have been yes. And we were really thinking about neurons in the hippocampus, this just sort of straight ahead memory-related area of the brain. But now we're in the basal ganglia, and things change a little bit. So think of it as kind of neuronal anthropology. We're in a different culture here. This is the culture of the basal ganglia. The basal ganglia doesn't want to deal with strengthening connections unless they know that something good has happened, when you were carrying out some actions. And in fact, you actually, in this scenario, there's a good chance you'll have fewer AMPA receptors. In order to grow more AMPA receptors, the striatal neuron requires an additional ingredient. So the additional ingredient is dopamine, that you might have guessed. You've actually got in the striatum not just AMPA receptors and not just NMDA receptors, but you've got dopamine receptors as well. And dopamine receptors we're going to represent by these little kind of yellow glowing receptors here. That's your dopamine receptor. All right. So the idea is, to begin with, imagine that the cortical neuron is releasing glutamate. Those are the green circles. Glutamate's binding. That activates the striatal neuron. Fine. And you complete the loop. If you activate the striatal neuron, if you complete that loop and you actually carry out the behavior, we were talking about, I wanted to make lasagna. So that's what's going through the loop, make lasagna. And now I actually make lasagna and it's rewarding, it's good. Let's assume it was even better, the lasagna, than I expected. So the dopamine neurons now squirt their dopamine into the synapse as well. Now, guys, I need you to sort of zero in on this. If I asked you, what caused the glutamate to enter this synapse? Those are the green circles coming from the cortex. From the point of view of what's going on in the situation in my mind, what is it that caused the glutamate to come into the synapse? That's right, the desire to carry out the goal. I think that would be a perfectly good way to put it, Stephanie. Another way you could even put it is to say these neurons in the cortex that are releasing glutamate here are activated as you're considering this goal. So you've at least got this goal in mind. And it may be that you're even feeling a desire for it. That's what's causing the glutamate to be released. You carry out the behavior, and the result is now dopamine surges. You observe in this person's brain the surge of dopamine. So now we can strengthen the synapse. If dopamine is released into the striatum, soon after I have this idea of wanting to make lasagna, if it's soon enough, or if those neurons stay active from the cortex to the striatum, releasing glutamate, if they're active all the while that I'm making the lasagna and I'm bringing it to my mouth, boy, that's good. So you've got all the ingredients. You can now strengthen the synapse. Okay, let me mention, guys, tactile, auditory, visual has to do with the fact that there are sensory stimuli. I'm in the kitchen. I hear my mother. That's auditory. Tactile, I don't know. I'm sitting on the couch. I can feel that I'm sitting on the couch. Visual, I can see I'm in my apartment. And then in the frontal cortex, I have this goal of making lasagna. So to be more specific, you could say that the glutamate coming from the cortex represents that whole combination. Wanting to make lasagna while I'm in the apartment, I hear my family, I'm feeling hungry, and so now if dopamine comes because the result was rewarding, really what it's going to strengthen is the ability not just to make lasagna, that goal, to become, more powerful in the future in terms of activating the striatal neuron, but to make that whole combination more powerful, and that is, when I have the goal of making lasagna and I see that I'm in my apartment and I hear my mother in the kitchen and I feel my hunger, all that stuff together, that's really the thing that now is going to get stronger. That's what dopamine is going to strengthen, essentially. Now let's suppose the goal is to press a candy machine for M&Ms. And that's being represented as, again, like we said before last time, activity in the prefrontal cortex, the very anterior portion of the frontal cortex. You've got a goal. All these goals are going to be there. Now, the auditory might be that I hear people in the neck, lounge, or, in that area where the candy machines are, the lobby, I guess. You've got visual, I'm seeing the candy machine, all that stuff. And together with my goal of pressing the candy machine for M&Ms, All of that together is causing glutamate to be released. It's binding to these AMPA and NMDA receptors, activating the neuron, the striatal neuron, enough so I complete the loop. I actually put the money in the machine. I press the button for the M&Ms. I get the M&Ms, and they're delicious, and the dopamine neurons surge. Dopamine surges out of those neurons. This was before. You had two AMPA receptors, and now the dopamine binds and the glutamate binds, and the next day, you've got more AMPA receptors, okay? And in fact, you don't even need to have the dopamine and glutamate the next day. They could have even cleared out, but you still have the AMPA receptors because that was what you're left with from yesterday's experience at the candy machine. Do all ideas form in the cerebral cortex? I would say that the general consensus, and you have to sort of come to a conclusion based upon these fMRI studies where you look at brain activity as people are remembering things or coming up with plans and so forth. So it's not simple, but I think that the consensus view right now in neuroscience is yes, that at least to be consciously aware of an idea, it's going to happen in the cerebral cortex. Now, the formulation of the idea may involve interactions between the cortex and the hippocampus and other areas and so forth. Certainly when you're accessing memories, which can be involved in bringing a new idea to mind, that would involve the hippocampus. And if you're imagining something and how good something was in the past, that'll involve the basal ganglia, or something you were afraid of will involve the amygdala. But in the end, to consciously have this idea that comes to your mind, you're going to need the cortex, Nice question.
If we have a goal in mind, right? That's one loop. We either perform it or we don't perform it. Does that loop continue to go until we perform it?
On the one hand, the loop that keeps the goal in mind, which is coming from the anterior frontal cortex towards the front, where these goals are generated, it really is true that that's a separate loop from some other loop that's going to be involved in performing the behavior. You need to have the goal in mind and keep that goal in mind in order to perform the behavior. Because if you have the goal in mind and that turns off, and you now start to perform the behavior, if you stop having the goal in mind, you might say to yourself, what am I doing? Why am I even doing this? So the idea is that even though there's going to be other neurons that become involved as you start putting lasagna in the oven and turning off, it's going to take more than just the goal to do it. But all that time, you're going to need to keep that goal loop, I'll call it. Yeah, you could say you're going to need to keep that active, because otherwise it would be like either you might, I don't know what the subjective feeling would be. One possibility is if the goal disappeared, that loop, right? You would be like, what am I, crazy? What am I turning on the oven for? And then if that loop started again, you say, oh, yeah, that's right, I wanted to make lasagna. That would be one. I mean, I guess the other scenario, I don't know, Isamar, whether this can happen with dissociative. I just don't know very much about dissociative episodes. But the other kind of everyday situation that you can imagine is I've got this goal in mind. You've got this sort of, I'm going to call it the I want lasagna loop. You've got it going while I'm like carrying out the behavior, and it could be another reason why that goal loop may stop is because as I'm doing it, I think to myself, you know what? I wanted lasagna, but this is just a big hassle. It's more effortful than I thought. My oven's not turning on, and you just sort of abandon the goal. So in order to actually get all the way to carrying out the full behavior, you need to have that goal maintained all the way throughout, really. And that means that when the reward outcome becomes clear that this lasagna was either better than expected or at least not worse than expected, you're going to have dopamine released at the same time that glutamate's being released by the goal neurons, because again, they really need to have been active the whole time in order to keep up your behavior to the end. All right. So let me look at Stephanie's question. I understand that glutamate first binds to the striatal neuron to carry a goal. After the goal is carried, you say dopamine needs to bind at the same time as glutamate. Is that the original glutamate that first bound to the striatal neuron, or is that a new glutamate? You're 100% right. You've got glutamate being released from the very beginning, way before the dopamine comes. At the end, as you carry out the behavior and you find that it's good, that glutamate is still going to be being released. And like you say, it's not the same original glutamate molecule that was first released during the first time through the loop. You're 100% right. It would have to be still going because the goal was still in mind. And there's going to be then at that point the glutamate and the dopamine together, and that's going to be enough to strengthen the synapse. You know, with the M&M it was easy because, like I say, I think I'll have some M&Ms. You press it, pop it in your mouth, and it's good. All right. There's not such a time lag. So let's go through this now. Let's say I have this goal of cooking lasagna, releases glutamate into the striatum, activates the loop enough that I actually carry out the goal. The loop keeps the goal in mind long enough to carry it out. The lasagna is rewarding, dopamine's released. Now you've got the right combination of glutamate, dopamine. You get your new AMPA receptors. Now that means that this synapse now is even stronger than it was before. So now tomorrow I think about making lasagna. Now thinking about making lasagna, let's say that means just that these neurons in the cortex flashed on. I think about making lasagna. Now with this extra AMPA receptor, I'm even more likely to be able to keep this loop going and not have it sort of just die out on me, you know, in the striatum. So here's really where it gets interesting. I'm deciding between cooking lasagna or watching a video. Which are we dealing with here? 2 loops, or are we dealing with 1? So now imagine I've got the idea of cooking lasagna, and you've got this loop potentially activating a striatal neuron, which potentially activates, you know, brain area 3 neuron, brain area 4, and which potentially keeps active the cooking lasagna goal. And then I've got my watch video goal, which activates some neuron or group of neurons in the striatum. And again, if it's successful in activating it, it activates neuron in brain area 3, brain area 4, and you complete that loop. So the question of which you're going to decide to do, because you can't do it both. I mean, you could if you multitask, right? But let's suppose you can't multitask, and you've got to either watch the video or cook lasagna. If you have to choose one to do right now, or at least one to start, how do you think about it? How, looking at this and thinking about what's going on in the brain, what's happening? How does the brain decide which to do? If you say, well, the one with the stronger synapse is going to be able to complete itself for longer, you know, maybe for a while they're both going, but one of them at a certain point can't compete. It just can't stay on long enough while the other one's staying on longer. There's some data to suggest that if one of these neurons become active, it actually has branches that inhibit its neighbors. So there could be a competition here. That the more this neuron's active, the more it inhibits this guy. And the more this guy's active, the more it inhibits that one. And that would really make it the case that the stronger synapse is going to win, because as this becomes a little bit stronger than this one also inhibits the other guy. You call that lateral inhibition, and a lot of, you know, it's a big thing in the brain. If you say the stronger synapse, you say, well, how did it become a stronger synapse? It became a stronger synapse because in the past, when I did the behavior, I reliably got a dopamine reward surge. And that's how it became a stronger synapse. So the one with the stronger synapse is the one that historically, for you, has been the one most reliably producing rewards. You don't necessarily need dopamine to be released as you're deciding. Because if dopamine was released every time you made lasagna and liked it, or every time you watch this particular video and liked it, that dopamine will have strengthened the synapse, produced more AMPA receptors. And today, all you need to know is which synapse is stronger, which one has more AMPA receptors. So in a way, the strong synapse tells you, oh, there must have been a lot of dopamine in the past when this loop was active. See what I mean? All right. If you look at these striatal neurons, guys, you got to keep clear now. Here's the striatal neurons. On the striatal neurons, what receptors have you got? Now, wait a second. Don't confuse us, right? On the striatal neuron means on the neurons that have their what in the striatum, their cell body. So if you look at the dendrites of these striatal neurons, tell me what type of receptors you're going to find on these dendrites. Yeah, nice. Okay, yeah. AMPA, NMDA, and dopamine, right? So now, imagine here's your AMPA receptor, and, like always, we do it in purple. You got your NMDA in red. You got your dopamine is glowing here. They each have it, right? If I watch a video and it's very rewarding, okay, if you had to diagram this, what would you show in this diagram to let me know that A, the person is watching the video, and if they're watching it, it means they must want to watch it. They must have the goal of watching it because they're doing it. And I want to know, how do I know that it's rewarding? So if glutamate was binding here, you could say, oh, the person actually is cooking lasagna. If glutamate's binding here, because this is where the glutamate's coming from, the cortex, you'd say, yeah, the person's watching the video. And if the glutamate was binding to both, you would at least say this person hasn't decided what to do, he's considering both, or he's doing both, that type of thing. Camila, go ahead.
Professor, hi, I just got a question. What if you got an idea and this is the first time you're doing something?
In order to do it, even to begin with, or to sustain this goal to do it, you're going to have enough AMPA receptors to begin with. So you can't have synapses with no AMPA receptors. They've got to at least have enough AMPA receptors that you could activate the loop.
So you can do activate the loop without DA in the beginning, and then you're going to either get it and do so again, or not get it and you're not going to return to this.
That's right. These synapses all start off somewhat strong. And imagine that being like when you're a kid, everything seems like it could be fun to do. You want to watch, who wants to watch a video? I do. Who wants to cook lasagna? Oh yeah, let's do that. It all seems good, right? And then what happens is the ones that you do and you don't get rewarded from, they actually weaken. The AMPA starts disappearing, right? And the ones that you do that end up being rewarding and producing a surge of dopamine, they strengthen. So you start getting more AMPA receptors in those. And pretty soon you've kind of sculpted your landscape of synapses so that the ones that are associated with the biggest rewards have a lot of AMPA receptors, and the ones that have never been rewarded, even though you've tried them in the past, they end up with so few AMPA receptors that it may be that they don't even produce enough loop activity to consciously even consider the goal anymore. Christopher, go ahead, buddy.
I got you. So I just wanted to ask if you were going to be uploading like a shortened version of this, just like you did with the other lectures and the last one as well.
Yeah, I'm planning to. What I'm going, they take me a little while to do. It turns out it's a little time consuming, although not completely. Partly to entertain myself, but believe it or not, I'm sort of like learning how to do this editing as I'm doing that.
I could tell you're having fun with it.
Well, I'll tell you what. I'll give you a little incentive to watch the next one. The one I'm working on, I just found out how to do like funny things, like to have my face really small and have it like peeking out over a neuron. So like once in a while you'll see Horvitz's face peeking out over the neuron or something. So
Oh, so wait, so your face is gonna be not the receptor, but the neurons?
Well, actually, I haven't gone total psychedelic here, but what I have done.
Yes, I'm just wondering what happened if a person who's very self-disciplined and he or she is just gonna do whatever things that's planned in, no matter it's enjoyable or not. like what happens?
Well, what happens in that case, Shuyi, what we think is, what happens is that would be a person, that's been somebody who's figured out a way, you know, with discipline to control their behavior without using the basal ganglia too much. In other words, the basal ganglia is going to tell you, oh yeah, just like eat the M&Ms. And the self-discipline is going to be that the basal ganglia is not my only way of choosing behaviors. I've got the ability to choose a behavior based upon more carefully thinking through consequences. And so that would be somebody who's got these other parts, probably of the frontal cortex as well, that are able to select behaviors even if that behavior doesn't produce much basal ganglia activity. Very good question. All right.